Imagine you're looking at a brain scan from an MRI machine. That image isn't just a random collection of pixels. It's a structured matrix, with rows and columns that hold specific spatial relationships. Now, imagine trying to classify these images to detect diseases like Alzheimer's. Traditional methods treat this data like a jumble of numbers, flattening the matrix into a long list of values. But here's the problem. That approach ignores the very structure that makes the data meaningful. This is where a groundbreaking technique called nonparametric maximum likelihood discriminant analysis, NPMLDA, steps in. Developed by researchers like Seungjun Oh, Seongo Park, and Hoyoung Park, this method is designed specifically for matrix-valued data that naturally comes in rows and columns, like images, EEG signals, or even stock market trends. So how does it work? Let's break it down. Traditional classification methods often assume data fits a specific mathematical structure, like being sparse, few non-zero values, or low-rank, simpler patterns. But real-world data, it's messy. These assumptions can fail, leading to poor performance. NPMLDA solves this by using a non-parametric approach, which means it doesn't force the data into rigid molds. Instead, it learns the structure directly from the data itself. Here's the clever part. The researchers used nonparametric maximum likelihood estimation, NPMLE, to estimate key parameters. Think of NPMLE as a flexible tool that adapts to the data's true patterns, rather than guessing at them. They applied this to vectorized matrices, essentially flattening the data but then scaling it with a special precision matrix to preserve relationships between rows and columns. This scaling step is crucial. By adjusting the data with the right precision matrix, the method retains the original structure while making it easier to analyze. Then, they used empirical Bayes techniques to estimate the mean values for each class, like averaging brain activity patterns for healthy versus diseased patients, without assuming those patterns follow a specific distribution. The result? A classification method that's both robust and flexible. In tests with real-world data, including EEG and MRI scans, NPMLDA outperformed existing techniques. It handled complex structures without needing manual tuning, and it didn't fall apart when the data didn't fit traditional assumptions. But what makes NPMLDA truly unique? Let's dive deeper. Unlike older methods, it doesn't rely on assumptions like sparsity or independence between variables. This makes it super adaptable. Whether the data is dense, full of information, or sparse, mostly zeros, the method adapts. In simulations, researchers tested NPMLDA against competitors like Sr-LDA and PMLDA. They created two scenarios, one with dense data like a detailed image, and another with sparse data like a sketch. NPMLDA consistently outperformed the others. When estimating a key part of their model, the coefficient matrix B, NPMLDA's estimates were closest to the real thing. Think of it like a detective who accurately reconstructs a crime scene, while others miss critical clues. In dense data, methods relying on sparsity failed to see the full picture, while NPMLDA captured both the main patterns and the noisy background. Even in sparse settings, it still nailed the details. The real test. Applying it to real-world data. Take the EEG dataset, which measures brainwave activity. With NPMLDA, we achieved the lowest error rate, meaning it was the most accurate at distinguishing between healthy brains and those affected by alcoholism. Then we tried it on MRI scans of Alzheimer's patients. In one test, NPMLDA perfectly classified early-stage V's non-demented brains, while others stumbled. In another, it still led the pack, showing remarkable consistency. So what's the big takeaway? NPMLDA doesn't need to assume your data is simple. It works whether the data is dense, sparse, or somewhere in between. This flexibility makes it a powerful tool for fields like medical diagnostics, where data is often messy and complex. And the future? Researchers are already exploring ways to extend NPMLDA to even more complex data types, like 3D brain scans or multi-layered datasets. Imagine a world where machines can adapt to any data structure, no assumptions needed. That's the promise of methods like NPMLDA. Next time you hear about AI or data science breakthroughs, remember, it's not just about speed or power. It's about adapting to the real, complicated world we live in. And NPMLDA is leading the way.